And the can is neutral. We have the rod is it's going to be charged. Based upon that right off the bat, you should be able to tell me what's going to happen. Interaction between something that's charged and something that's neutral. It's going to be polarized. But if you guys remember yesterday, we did the paper. The roll of paper. Yeah, was it very cool?
It was quite cool.
It was kind of lame, okay? The paper barely moves. Well, on this one, we get something a little bit better.
Don't let him touch.
Okay?
On.
Okay. But you can see this is way better
And paper.
than the paper.
Are they attracted?
No,
they're
they're
repelling.
repelling.
Hey guys, come on. Yes, it's attracting. You can see whatever way the
No, the rod camera.
yeah. So good point. Is the rod touching the can?
No.
No. So our charge is being transferred.
No.
No, all we're doing is we're taking the charges that are already in here and just shifting them around. But why did this work so much better than this?
Because it has a defined shape.
Metal is.
Well, okay, fine shape, but even more than that, there's a fundamental difference between those two materials.
Metal's a conductor.
And it comes back to it being a conductor. So in order to fully really get down to why this is important, we're going to diagram. I'm going to turn off the projector.
Won't it be the same diagram as the rolled piece of paper?
Similar.
Almost. But we're gonna, the difference is why it's the differences between them is what makes it better.
It's the conductor, there's so many differences.
Correct. So we start out, and now a conductor, I'm just going to draw in. We don't need to worry about the atomic model when we're talking about the can. The reason why, here I'm going to say it's net neutral. It's also a conductor, and it's non-polarized. So next picture. There's my negative rod. So this is net negative. Here's my can. You have a freebie. What cannot move?
Proton.
Protons. So I have 1, 2, 3, 4, 5, 6. But think like an electron. The electrons that were right here, are they going to want to just chill out by that negative rod? No. What are they going to try to do, Jeremy?
Get away. Rip down.
Just get away a little bit?
Oh, as far all the way to the
They
side.
They'd like to go as far away as possible. And Ricky, this is where we pull in the difference. When we were dealing with the paper, the only thing you could do is shift within the atom. Now, the electrons that were here can go all the way to the back side. The electrons that were here can go all the way to the back side. Now, is every single electron going to leave?
No.
No, maybe we'll leave one over there. But other than that, almost all the electrons in our diagram, they run away. Leaving this side,
Should we draw all the electrons in at the opposite side?
yeah, they have to go somewhere. That side's left local positive. This side will be local negative. Overall, what is the can?
Neutral.
It still is net neutral.
And it's,
Last thing we need to look at is what is the interaction that happens. Well, I have negative, and it's really close to a positive.
it's the trap.
It's going to attract. That's what causes the can to roll.
Okay, like what would you want for words about that? Like I don't
You don't show it.
So if I were writing out in words, I would say the can starts neutral, it's conductor, and it's non-polarized. When I bring a negative rod close, what happens to the electrons, Ellie?
They move as far away from the negative
The
rod.
electrons move far away, leaving the close side
Local positive.
local positive, making the far side local negative.
So would it be polarization?
The rod and the local positive, yeah, so making it
Is
polarized.
this polarization?
Making it polarized. The net negative is closest to the local positive, so it attracts rolling the can.
Is this,
And this is polarization. The reason it is, I'm taking something that is neutral, and all I'm doing is I'm shifting
To charging.
the charges within the original object. I'm polarizing it.